Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about the synthesis of glycosylidine diazerine. So this type of the point we have covered in our previous lecture while discussing that synthesis of glycosylidine diazerine, what kind of the molecule it is, how it can be synthesized from, starting with what type of the material used for the synthesis or for the achievement of glycosylidine diazerine with the help of suitable example. After synthesizing that glycosylidine derivative, we also discuss the application of that, how we can convert glycosylidine diazerine into other product, other organic compound, mainly as a carbohydrate, that we have learned. So while synthesizing, there we have taken as a material, and we also focus our main notable point is at an anomeric hydroxyl group. All other part of the whatever hydroxy groups are there, they are the protected one with that benzyl group, and we go on adding the reagent number 1 to 5 we have achieved as a compound number 7. If you observe the compound number 7, you will find there is a 3-membered nitrogen containing double bond at an anomeric carbon atom, and that derivative is nothing but as a glycosylidine derivatives. By starting with the different starting material, we have derived the 2 glycosylidine derivative. Another way we have achieved the diazerine derivative, the starting material there we have taken is anomeric hydroxyl group is not, we have shown staggered manner, and other at carbon number 2 there is a protection of NHAC, that group, and other rest of the group are protected with that benzyl, that is compound number 8 we have considered, and we have added the reagent number 6 onward, 6, 7, 8, 9 and 10. Finally, we have got the product is a diazerine, glycosylidine diazerine, and after that taken as a glycosylidine coupled with other derivative of that glucose unit, and we will get as a different derivatives. In that way we have learned details of that compound. Now the last point remaining in this chapter is because the synthesis of glycosides. So here the last point remaining as a alkylation of the reducing sugar. How do we define alkylation of reducing sugar, or other way round, or in the other word, reducing sugar means what? Whatever the sugar chemistry is, because that the sugar unit generally at an equilibrium they are present in the cyclic form, and that cyclic form of that, specifically basic unit of that carbohydrate D-glucose, is mainly present in the mixtures of alpha and beta. Alpha and beta are known as anomers of each other. Anomers, at an anomeric carbon atom, there is a change in, they differ in the configuration at anomeric carbon atom. That type of the structure are known as anomers of each other. Anomers and the epimers are the two different terms. They are totally different. The epimers are the word used when the sugar generally as a D-glucose represented structure. Open chain structures are generally represented according to as a Fisher projection formula. If you observe the open chain structure of that D-glucose, you will find in D-glucose and another one is a D-mannose. They differ at the at only one chiral center. So that type of the structures are known as epimers. Another one, D-glucose and D-galactose, they are also epimers of each other, because both are, you have to consider according to as a Fisher projection formula. Observe these two structure carefully, and after observing, what do you find? Everything is the same. Connectivity of that carbon atom also has the same. Chiral center also has the same, but they differ only at a carbon number C4. Glucose has a hydroxy group on right hand side. Whenever there is a one streak, always remember, when the hydroxyl group on the right hand side, that chiral center must have R configuration, and at the same time, if you observe the structure of galactose carefully, at a carbon number 4, you will find there the hydroxy group will be on the left hand side. It means the configuration of that chiral center must be S configuration, and therefore these are two structures. The relationship between two structures, D-glucose and D-galactose, are epimers of each other, and anomers just now we have seen. So now the question, finally, is a reducing sugar. How do we define reducing sugar, or what do you mean by the reducing sugar? Let's see over here. Reducing, if you remember the three commonly observed disaccharides, let me recall here. Number one, sucrose, commonly observed disaccharide. Second one is a maltose, commonly observed saccharide. And third one is a lactose, which is present in the milk. So if you see how that disaccharide, it means two sugar unit combined together and form the structure which is known as a disaccharide. The starch, that is a sucrose, is one of the disaccharide. If you observe the structure carefully, you will find over there the sucrose is made up of by one glucose unit, and another one, second one is a fructose unit. Fructose and the glucose are isomers of each other. Isomer means, as we know, that having same molecular formula but different structures are known as isomer. In a D-glucose, if you observe carefully, you will find there are the 4 chiral center. If you observe the structure of D-fructose, you will find there are only 3 chiral center containing one additional carbonyl group. And as we know that carbohydrates are, there are the various definition for the carbohydrate. Carbohydrates are polyhydroxy aldehyde or ketone or a compound which gives rise to sugar unit on hydrolysis is known as a carbohydrates. Or other way round, we can define the carbohydrates. Carbohydrates are polyhydroxy optically active containing aldehyde formyl group and the ketonic group are known as carbohydrates, and that are the various definition. We already know that, but here, and if you observe the structure of that sucrose, which is a non-reducing sugar. Why it is a non-reducing sugar? Because it does not contain hemiacetal structure. Hemiacetal structure, if you remember your previous classes chemistry knowledge, the aldehyde group when treated with the alcohol, the resulting compound form as a hemiacetal means hydroxy group and the alkoxy group, both are present on the same carbon atom. That type of the structure generally in the organic chemistry are called as a hemiacetal. And when both the functional groups are present on the same carbon atom, it is a very unstable. By just treating with the treatment given by that acid, again it revert to get the aldehyde back. So same thing, whenever there is a cyclic form of that disaccharides, if you observe the fructose unit as well as du unit, when there is a glycosidic linkage is formed, it utilizes at least one of the anomeric hydroxyl group for the formation of the glycosidic linkage and form as a disaccharide. And once they form as a disaccharide, then again observe, is there any hemiacetal structure is present? If no hemiacetal structure, which immediately open chain means there is a aldehyde group. Aldehyde group can give the positive Tullien's reagent as well as filling test. These are the two tests are positive shown by that sugar unit. So that kind of the sugar, maybe as a monosaccharide, disaccharide or polysaccharide, they shows the reducing property, means they are the reducing sugars, and those do not contain that hemiacetal structure in their compound. They do not show, they do not give positive Tullien test as well as filling solution. Both tests are coming negative, and therefore that type of the structure are non-reducing sugar. So sucrose is a non-reducing sugar because In a glucose unit, anomeric hydroxyl group is utilized for the formation of the glycosidic bond or glycosidic linkage. In the fructose, it utilizes its hydroxyl group, and there is a elimination of water molecule takes place, and the resulting compound formed is a disaccharide. Another example or the second molecule will be the maltose. If you remember our previous lecture, there we have seen how the maltose disaccharide is formed. It is made up of by 2 units of glucose, and there is a formation of glycosidic bond. And as we know that how the glycosidic bonds are formed, utilizing one of the anomeric hydroxyl group and the other hydroxyl group of other unit, and there is a elimination of water molecule takes place, and the resulting compound obtained is known as a maltose. And if you observe this structure carefully, there you will find there is a hemiacetal structure is present, and that due to the presence of hemiacetal structure, that gives the positive filling test as well as Tulin test. Another third commonly known compound, known disaccharide, will be the lactose which is present in the milk, and this lactose is made up of by one galactose unit and the another D-glucose unit combined together with the elimination of water, and there is a formation of the glycosidic bond, and the resulting compound form is called as a disaccharide. In the same way it is formed over there. So this is all about, and this maltose also is a reducing, it shows as a reducing property, means reducing sugar. Similarly, if you see the polyhydroxy compounds, there is no hemiacetal groups are present, and therefore starch, then another maybe as a cellulose or glycogen, these do not show as a reducing properties. So that type of the thing we have seen. Now let us, what we are going to discuss here, the alkylation of the reducing sugar. Here just now we have seen as an introduction regarding that. Now the alkylation of reducing sugar, that is a glycosylation methods. The method for glycosylation generally contain a procedure for activation of the anomeric position. Scheme first shows two possible procedure for formation of the glycosidic linkage. Let me show you the two procedure. One is a conventional glycosylation. First one is called as a conventional glycosylation. Glycosylation. First one is a conventional glycosylation. Look at here. This is one of the structure I am showing over here. This is a triggered bond. L indicate as a leaving group. Now this ring, you can call it as a ring, and which the here you can remember it is a promoter, promoter, and now this can be act as an electrophile here. Electrophile, there is a exception. This electrophile act as an donor, whereas another structure I am representing over here. See this one. Now here is a hydroxy group, and now this ring you can call it as a B ring. So you can show these two rings in a box so that you can remember that in a better way. Now this is also shown in the box, and now here the lone pair which is going to attack on that carbon atom, there is a departure of leaving group in this way, and the bond will be formed here, this one O. Now this bond O, and now here I am representing these rings separately like this. This will be the A ring, this will be the B ring, and now this we can call it as a B is one of the method. It is, this ring is known as a nucleophile. One is known as a nucleophile, and here this nucleophile act as an acceptor. Nucleophile act as an acceptor over here. That nucleophile act as an acceptor, where this electrophile act as an donor. Here is some exception is there, and after that we are getting the product generally like this, and here this is a B method, that is a conventional glycosylation. We got this type of the product over there. Now let me show another one, glycosylation by a new concept. Glycosylation by a new concept. This is another glycosylation by a new concept. Now by using this concept, let me draw here another structure. The structures are like this, O, and here M stand for as a metal, and now this we can call it as a, and this species act as an nucleophile in this case. It is nucleophile. Here it is acting as an nucleophile, and then there is this ring, and where here I am representing there is a L. L is nothing but as a leaving group. This is a, this will be the B, and after combining together we are going to get the product, this one O, then this will be the B ring, this will be the A ring, and now here this is the formation, so this will be the A bond formation. And now what is going to happen here, this is going to attack over there, and L is a departure. After departing, this act as a nucleophile, and this is act as an electrophile here. Electrophile, as we know that. When nucleophile attack at the center, there is a departure of leaving group, and where this is a scheme number first. This one is a scheme number first, and that represent conventional and new glycosylation method. Conventional and new glycosylation method, and where L is called as a leaving group, and where M is called as a metal here. M is known as a not method. M is known as a metal. It is a metal. So there are the two clear-cut schemes are shown over here. One is a conventional glycosylation, and whereas another one is a glycosylation by a new concept. And conventionally, the specific affinity of a leaving group at the anomeric position and a suitable promoter accelerate a coupling reaction on as described in the previous here, and as a result of glycosidic bond is formed by nucleophilic attack of a glyconic oxygen, that is a B part over there, and we can also form the glycosidic linkage by nucleophilic attack of anomeric oxygen by A route, and this glycosylation procedure retain the anomeric oxygen A in the glycosidic bond. R. Smith and P. Kovac, these are the scientist name. R. Smith and P. Kovac introduced the reverse concept to glycosylation method and develop anomeric O alkylation and glycosylation via locked anomeric configuration respectively, and these methods of which general procedure are shown in the scheme number 2 use different approaches for stereo control of glycosidic bond formation. Let me show you how they, after the alkylation, how that compound becomes as a non-reducing. So that type of the, and after that we are going to measure whether they are reducing sugar or non-reducing sugar after the O alkylation. Suppose we have a general reaction over here. Here is a generally PO, phosphate containing compound, generally I am showing over here, and there is a O, M is a metal once again over here. At an equilibrium, this may be shown as a conversion. This group may be shown like this. O, here we can show this methoxy group like this. The M is stand for as a metal once again. This is a nucleophile. This is act as an nucleophile, and then this is a nucleophile, and after that when it is treated with the reagent like as a TFOR, that is electrophile. This is a nucleophile which is a electrophile, and you are going to get the product, this one, that is here written as a OR, that is a PO over here. And now look at anomeric carbon atom, there is R is attached, therefore it is a non-reducing sugar. So anomeric O alkylate, this is known as a anomeric O alkylation. Once it becomes as a O alkylation, it shows as a non-reducing property of that compound. For example, let us take as an example over here. So let me clean this first, and now I am going to show you the another example. Other way around, we can show over here. This is a structure I am showing over here. Here O, then O. Here may be as a SN, then butyl group. Here also as a butyl group, and here as usual is a PO, and this is act as an nucleophile here. This is a nucleophile, and when this nucleophile treated with the RX, which is act as an electrophile, and the product obtained, which is this kind of the product we are generally going to get. Here is a OR, then OR, here a hydroxyl group, and this PO as it is, and this is called as a glycoside, and this is we got as a glycoside, and this shows as a non-reducing properties because there is no hemiacetal structure in this case, and that's why they are the non-reducing sugars. When the alkylation takes place, that becomes as a non-reducing sugar. So remember this alkylation of the reducing sugar. And glycosylation via locked anomeric configuration scheme 2, generally procedure for the anomeric O alkylation and glycosylation locked anomeric configuration that we have seen with the help of this example. And the anomeric O alkylation method utilizes an anomeric sodium or potassium alkoxide as a nucleophile. Stereoselectivity in the coupling reaction depend on the different reactivities of the anomeric alpha and beta anions. Factor controlling the reactivity such as conformation of the nucleophile are described in a detail. Review article by Smith have described the anomeric O alkylation method. Just now we have seen in the previous scheme. Glycosylation via locked anomeric configuration employs a stannylene acetal at the 1,2 position of the hemiacetal. The stannylene acetal fixes the anomeric oxygen in the 1,2 cis configuration and leads to 1,2 cis type glycoside, which we have seen just now. This is a glycoside, right? Glycoside, and in addition to temperature, solvent, promoter and additive, we must consider the configuration of the nucleophile, including roles of substituent groups and the activity of the electrophile primary compared with the secondary triplates. And this section describes the factor that led to the stereoselective coupling reaction. I think with this we have completed the point number B over here of the syllabus, and tomorrow onward we are going to start or discuss the synthesis of dry saccharide, trisaccharide and the polysaccharide with the following by considering the following point, like as a stereoselective synthesis of the beta monocytes. I think with this let us stop today here. Remaining we will see in the next lecture. Thank you. Have a nice day.